Today's video will demonstrate the class diagram of the binary search tree. Hello, I'm James Helfrich. The binary search tree is not one of the built-in containers provided with the standard template library, but rather it is the underlying data structure of both the set and the map. This video will explain how the class diagram for the binary search tree works. The binary search tree consists of a collection of BNodes and a companion nested class. So the binary search tree is a class called BST, and it has a default constructor, which is an empty tree, and a copy constructor, and don't forget the destructor. Now, you can use a variety of other constructors if you like. For an example, the initializer list constructor, the move constructor, or the iterator constructor, as many of these as you like. You can equally implement them here or in the set and the map class. It doesn't really matter how you do it. We also have a destructor, and the destructor will destroy any nodes that are in the binary search tree. Of course, we have an assignment operator to copy one BST to another. We have the size, empty, and clear functions as well. Next, we can insert a single element. But what's the data type of the element? It's of type T. And T is not an integer or float or a string, but could be anything. In fact, that makes BST a template class. And we indicate it's a template class with a T in the upper right-hand corner. Erase takes an iterator. The iterator is a nested class within the BST. Notice how we indicate it's a nested class with a pinwheel connector. Now, this is a public nested class. In other words, the client has access to the iterator. We also have find, which takes a T as a parameter and returns an iterator. Begin and end with both return and iterator. Now, our BST has a member variable called the number of elements, and this is an integer. And it also has a pointer to a BNode, and that's the root. And we indicate that BNode is a nested class with the pinwheel operator as well. Now notice this BNode nested class is a private nested class, whereas the iterator is a public nested class. In other words, the client has access to iterator, but not direct access to the BNode. There is no way to indicate public or private for nested classes in a class diagram. Now our iterator is going to have a default constructor, it's going to have a copy constructor, but it would also have a non-default constructor taking a pointer to a BNode. And this allows me to create an iterator from any node that I like in the binary search tree. We have the equals and not equals operator to determine if two iterators are pointing to the same node. We also have the increment and decrement operator, allows me to advance or decrement the iterator. And we have the dereference, and this dereference will give me a T. The iterator has a single member variable called P, and P points to the B node. So in other words, it does not contain a B node, but rather a reference to the B node. Now we can have 0 or 1 references. 0 if I'm the end iterator, and I have the null pointer, and 1 if I'm pointing to an actual B node. So let's take a look at the B node. The B node has a default constructor and a non-default constructor taking a T as a parameter. Now notice I do not make B node a template class, because it's a nested class within the BST, therefore I take the BST's T rather than my own, which requires me to have a single member variable called data, which is of type T. I also have a pointer to left, pointer to right, and pointer to parent. And this means I have a reference to 0, 1, 2, or 3 other B nodes. There's 0 references if my B node is the root and the only element in a BST. 1 reference if I have only a parent, in other words, my B node is a leaf. I can have 2 if I'm both a parent and a left, or the root maybe have 2 nodes if I have both a left and a right child. And 3 if I'm somewhere in the middle. I have a parent, a left, and a right. I also need to have another member variable called isRed, and this keeps track of my red-black balancing. I'm either red or I'm black. To help with the red-black balancing, I have 3 helper functions: verify red-black, verify BST, and balance. Balance will do the red-black balancing. Verify will determine that my binary search tree honors the BST constraint. The left node is less than or equal to the current node, which is less than or equal to the right node. And verify RB, red-black, is going to make sure that my red-black tree is properly done. The 2 verifies are debug-only methods that I use to ensure that I don't have any bugs, but the balance I'm going to use all the time when I insert and remove elements from my binary search tree. I also have 3 helper functions: delete BNode, delete binary tree, and copy binary tree. These are all private, And the reason why I'm using them is oftentimes it's more convenient to walk through a BST recursively than is through an iterator. So clear, for an example, is much easier to implement for recursion with an iterator. And my delete binary tree will be called from clear, and that's going to be a recursive call. Delete BNode and copy binary tree are going to operate much the same way. You can learn more about the BST, including red-black balancing and iterators, in the BST chapter of the C++ data structures textbook.